the atomic structure or defining the atom. An atom is the smallest particle of an element which retains its own identity in a chemical reaction. In other words, an atom is an entity that retains its identity throughout any chemical reaction. Molecules change, but atoms retain their identity and chemical physical properties. Early thoughts. Democritus held that atoms, from atomos, not cuttable, were indivisible and indestructible. While this notion could explain some physical phenomena, chemical behavior was not described. The earliest philosopher, friend of wisdom, to consider the possibility of discrete forms of matter was Democritus. John Dalton. He was alive from 1766 to 1844. He revived the idea of atoms and made some basic assumptions about the reality of atoms. Using an early form of the scientific method, Dalton renewed Democritus's ideas into a form compatible with experimental observation. Here's a chart of what he described. Dalton's atomic theory is summarized in 5 statements. Atoms are small, indivisible particles. Atoms of the same element are identical in physical and chemical properties. Different atoms can be mixed physically and react chemically in integral numbers to form compounds. A chemical reaction joins, separates, and rearranges atoms. Atoms of one element cannot be transformed into another element. These statements are still true today with the exception of the 5th postulate. Atoms have been transformed into one another by nuclear reactions, but not by chemical reactions. We can also say number 1 might be not true today. We have found that there's smaller and smaller particles within the nucleus of the atom. Atomic size is measured in terms of the radius of an atom. Most atoms fall in the range of 0.5 times 10 to the minus 10 meters to 2.0 times 10 to the minus 10 meters. That's pretty small. Modern instruments allow an observation of individual atoms under certain favorable conditions. Here's a structured table of ideas and standards and vocab that you might run into. Subatomic particles. In the hands of chemists, Dalton's atomic theory is broken down further into 3 particles common to all atoms: electrons, protons, neutrons. Each of these particles we shall deal with in turn. Question: are these particles, electron, proton, neutron, truly elementary? Electrons seem to be truly elementary point particles. They have no measurable radius and extremely small mass. The proton and neutron are made up of more elementary particles we know now, named quarks, and some other terms. Electrons. The cathode ray tube helped to discover the electrons. They were discovered by J.J. Thomson in 1897 using this apparatus. A cathode ray is a tube and was attracted by a positive magnet and repelled by a negative electric charge. Because he knew opposite charges attract and like charges repel, Thomson concluded that the cathode ray was composed of negatively charged particles that were later named electrons. Those particles went to the positive magnet and were repelled by the negative. Milkian oil drop experiment. Since the Thomson experiment only determined the charge of the electron, another independent experiment was needed to determine the quantity of charge carried by the electron. By observing behavior of charged oil drops in a variable electric current, the oil drop experiment determined the charge on the electron was 1.602 times 10 to the minus 19 coulombs. This is one of the 7 fundamental units of the SI system. From this value, the mass of the electron was determined to be 9.11 times 10 to the minus 3 kilograms. Milkian's actual experiment apparatus is shown here. Protons and neutrons. Protons were discovered in an apparatus by Goldstein, similar to the Thomson experiment. When electrical current was passed through a partially evaluated Thomson apparatus filled with hydrogen, protons were collected at the anode or negatively charged end. Neutrons were confirmed by Chadwick. Neutrons have no charge but a mass similar to protons. The properties of particles are given in tables in your book. That page number probably not accurate for your current book. Note the relative mass of the electron as compared to both the proton and neutron. Atomic nucleus. J.J. Thomson had a picture of the atom where electrons were embedded in a pudding-like substance, which was referred to as the plum pudding model. It's after an old-fashioned term of a cake in New England, kind of like a fruit cake. The plum pudding model was proposed by Kelvin and J.J. Thomson. Electrons were seen being randomly distributed in a sphere of positive charge, kind of like a chocolate chip cookie today. Rutherford proposed a new model of the atom that included mostly empty space and a central positive charge. The nucleus is the tiny central core of the atomic or the atom, composed of protons and neutrons. In Rutherford's gold foil experiment, a stream of heavy charged particles were aimed at a thin piece of gold foil. The plum pudding model demanded that all the particles should pass through uniformly through the gold. But Rutherford's experiment showed that a few particles were deflected. The explanation was that the atom is mostly empty space with a positive charge concentrated in a very small region at the center of the spherical atom. Here's a graphic of what he did and what he found. In the nuclear atom, the protons and neutrons are located in the nucleus with effectively all the atomic mass. The electrons are distributed around the nucleus and occupy almost all the volume. Here's some vocab that we'll cover in this section. Distinguishing between atoms. Atoms are composed of protons, neutrons, and electrons. Electrons surround the nucleus, which contains the protons and neutrons in a sort of cloud. Elements are chemically different because they contain different numbers of protons. Atomic number is the number of protons in a nucleus. Mass number is the number of protons plus the number of neutrons in a nucleus. If you wish to know the number of neutrons in a nucleus, subtract the atomic number from the atomic mass. The standard shorthand for writing an element looks like this. Helium is the atomic symbol. 4 at the top is the mass number. 2 at the bottom is the atomic number. You can also do the atoms by using the mass number and the name. For example, in the helium atom above, you can write helium-4, where the 4 is the mass number. Isotopes are atoms that have the same atomic number of protons, so it's the same element, but a different number of neutrons in their nucleus, thus different mass numbers. Because these protons have the same number of electrons and protons, they have similar chemical properties. Some of their chemical properties have some different details, especially in the rates of chemical reactions. In chemical literature, isotopes are sometimes written with the element symbol followed by a dash and a mass number. Example, 3 isotopes of oxygen can be given as oxygen 16, oxygen 17, oxygen 18. So the 16, 17, 18 are the mass numbers. When referring to the mass of an element, it's convenient to write the quantity in terms of grams per atom. In practice, relative masses of atoms are compared to an internationally agreed standard. The standard is the isotope C12. Isotope mass number equals 12, exactly the elemental carbon, resting in its electronic ground state. The value assigned to this atom is 12.00000 AMU, where AMU is referred to the atomic mass unit. Other elements and their isotopes have their atomic mass units calibrated against this standard. The 3 known isotopes of hydrogen have the following masses: hydrogen 1, 2, and 3. Hydrogen 2 is also called deuterium. Hydrogen 3 is sometimes called tritium. The actual atomic mass of an element is a weighted average of the individual atomic masses in the element's isotopes. We will visit the topic in another unit, but just a couple of points about the periodic table. The elements are basically arranged in order of increasing atomic number. The detailed configuration allows comparison of elements with regard to similarities and differences. The configuration will ultimately be explained in a future chapter after a quick look at quantum mechanics. Periods are rows of the periodic table. Families, also known as groups, are columns. The end.